The AI experiences that you might be playing with daily might actually not be one model, it might be multiple models. This compositional setting is messy.
They're really black boxes to us, meaning we still don't really understand what happens inside of them. And I really view this space as one of the emerging frontiers of deployability of AI.
AI supply chains is this term that refers to this new setting of AI training and deployment and use that's compositional. So rather than one model that is trained in this isolated, siloed setting, now you have something I'm going to refer to more like a system of systems. Multiple models chained together, glued together in various different ways into one AI experience or system. What we used to do when we evaluated traditional machine learning models was we'd benchmark them and we'd figure out if they're reliable for that particular setting. We're no longer just applying a model to one setting, we're often applying it to many settings, and we haven't historically studied AI systems in this particular way.
AI models are no longer built by one team for one purpose. They are trained by one organization, distributed to another, modified by a third, and ultimately deployed by someone who never saw the original code. Even the people who train AI models don't fully understand what happens inside these black boxes. Multiply that uncertainty across a chain of handoffs and fine-tunings, and you have a system where accountability is diffuse and behavior is unpredictable.
When we now enter into this world of AI supply chains, we still are kind of beholden to the behavior of the resulting model. Maybe we want to resell the model that we adjusted to our applications to someone else. And then that other person now has this black box. Now you have the system that, like, even when you control everything was already kind of hard to exactly control and specify, now has this distributed control across this whole supply chain, and we need to deal with that. This is a real issue, and it's affecting us right now. It forces us to think both from a technical perspective, but also from legal and regulation perspective of, like, how do we square the circle? Like, essentially, how do we think about accountability, about responsibility, when we have, again, this diffuse process that gives rise to the final model that we are deploying, especially in the context that are very real-world facing and kind of have some real-world consequences.
When you build on top of someone else's AI model, you inherit a dependency that changes when upstream providers improve, retrain, and update them. When a model in the middle of your pipeline changes, the effects ripple downstream. When something goes wrong at the end of your chain, identifying where it went wrong and why requires untangling a web of interdependent systems.
At first, we need to, again, recognize that this is happening, and there might be this mismatch between the downstream developing objectives and practices and the upstream ones. Maybe you need to have an agreement with someone who delivers your models to give you heads up, at least, that this has happened. And the other kind of very important thing to do is to actually be very precise, or as precise as you can, about what the desirable behavior of model is. I will talk to my provider saying, hey, I really need this to happen. What are the goals that you are trying to meet? What they can guarantee for you, and which part you need to deliver yourself. And that over time will lead to both developing the technical solutions for the systems and technical tools to guard and kind of make sure we adhere to the specification. And this is not just actually just a one-shot checks at the delivery of the model. It has to be a constant monitoring and kind of thinking, okay, how will I know if some qualities of the models will drift away from the desirable goals?
You might need an explanation for why your AI system made a decision or gave an output. And you might not necessarily have access to the intermediate upstream dependencies that exist. What you'd want to be able to do is build an explanation that accounts for this composition of these systems. And you do this by taking the explanation of model A, and then model B, and then model C, and you put them together. Each time you do a local explanation, there might be a little bit of error, and the error can accumulate with each step. It's a little bit like a game of telephone. It can be multiple things happening at once that have to be pieced apart and fixed in order to resolve the issue. And what our end goal should be is to be able to look at these systems as complex systems and isolate where these different errors are coming from and kind of verify and respond to them as a composed system.
Decisions made by modern AI systems can produce or come with multiple types of outputs, like an explanation, an output like a text string, a verdict, or classification. In a simple system, you can trace that artifact back to its source and verify it. But in a supply chain, that artifact is the product of many upstream decisions, compounding across models that weren't necessarily designed to work together. Artifacts can look correct even when they're not. The output is coherent, but the answer is wrong. What does that actually look like in practice?
We don't have norms and best practices for how to think about these settings. So in a financial setting, you apply for a loan, you get an explanation for why you weren't approved for this loan. The explanation in a really long supply chain might be incorrect. It might tell you, oh, don't pay off your student loan. This is one of your longest lines of credit. If you pay off a large portion of it, it might be helpful, or maybe actually paying off the loan entirely will improve your credit, right? So you might be told to do something that's opposite of what you should actually do because the error accumulated so substantially. Another case study that we look at in this paper is on how upstream decisions that model developers make can introduce constraints downstream. For example, you might have a model that learns the concept of doctor, and you want it to not associate with a particular gender. It changes the way that the model is learning about this concept, and it also changes the underlying geometry of the representations. So you can introduce a bunch of these types of constraints upstream, rules, if you will, and then you go downstream and you let someone use your model. And this particular model needs to be able to differentiate gender for some reason, and it happens to care about profession. What we show is you can actually unlearn that upstream constraint, so you can force a rule upstream, and you can undo that rule downstream. But when you do the unlearning, it's at a cost. What we've shown is that what you learn upstream limits what you can do downstream, and it does so by kind of shaping the geometry of the representations that you care about. And so if you want to do the unlearning, you have to have more energy to push against that. This is a new algorithmic challenge that is just surfacing in this AI supply chain setting. It's really interesting, and we're hoping that more people will kind of collaboratively work on fixing it. I think what's really interesting that we're doing a little differently as compared to when people describe models with metadata or model cards is that these are kind of descriptions. They fall almost under the equivalent of a manifest. If you're a cargo ship, you have a manifest of what's in the cargo. Well, just because something says what's in it doesn't mean that that's actually what's in it. And so we're kind of pulling on these methods to inspect internally the cargo. What is a model learning, and how does that have consequences on all these different applications, whether you're adapting that model downstream or you're gluing these models together, you're ensembling or otherwise composing them.
Yeah, I'm not saying here we should not have model cards. It just means that they are not a full solution here. You need more specificity here, which honestly cannot really come in the form of a couple of sentences. It has to be probably some more digital artifact that you're able to examine.
I'm guessing in proprietary, closed model settings, the model cards are really robustly managed. But when you look at open models, they can just be all over the place.
I see a world in which our work and other people's work will actually evolve what model card means. It will no longer be just a document. It will be also, again, something that has some measurements, some maybe API for checking some things, like how this maps onto your system.
We've studied explainability, fairness, and constraints, and we're looking at this application space of what does it mean to have problems when you update a model, who is impacted by it, and how can you flag whether or not you want to fix those problems. I think this is just such a rich space of study, and I hope that we can continue exploring it to get to that idea of potentially verifiable goals. I'm Aspen Hopkins. I'm a PhD candidate at MIT, and this is
Aleksander. I'm a professor at MIT and also Aspen's advisor.
And this is MIT CSAIL.